So presenting, we've got Clay Jones. He's a geologist and research scientist at the Energy and Geoscience Institute. Your speakers. Say that. Okay, go ahead. All right. He's at EGI at the University of Utah, where he started in 2004. He holds a bachelor's, a BSc, an MSc, and a PhD in geology from the University of Utah. Clay is the chief geologist for the DOE-sponsored Utah Forge EGS Research Laboratory. He was also the TA when I took Intro to Earth Systems class. So I'm not saying he had a big influence on me at that time, but he was a great TA. Clay's primary research focuses on, the mineralogy and geochemical evolution of geothermal reservoirs. He studies secondary minerals to understand reservoir geometry, fluid rock interactions, and the chemical thermal evolution of reservoir fluids. His work in petrography, X-ray diffraction, electron microscopy, yep, said that right, and isotope geochemistry gives insights into permeability structures and their influence on geophysical surveys. He has conducted geothermal reservoir investigations worldwide for government and private organizations, including the DOE and various energy companies. All right, let's all welcome Clay.
Okay, thank you. We're getting there.
Yeah, what's it?
Okay, we're going to talk about characterizing reservoir rocks at Utah Forge. We're going to be talking about lithologic complexity within granitic gluton, and also get into a little bit the natural fracture now at the Utah Forge site. So let's just jump in. Here's our introduction. We've got our geologic map over here. We've got the Utah Forge site outlined in red. We have our deep wells plotted on there. What you're seeing here are the yellows, kind of tan colors are the basin fill. Then we're going to move over to the outcrops of the Mineral Mountains. It's the largest batholith in Utah. Let's do it. So we're going to go from these really old metamorphic rocks in gray, the PC, those are 1.7 billion years old, moving into the light blue, which is a 25 to 26 million year old granodiorite, then up into the greens, oranges, and blues, or not blues, just greens and oranges. Those are the plutonic rock. They were assembled between like 17 and 22 million years ago. And sitting on top of that are the pink colored rhyolites that are between 450,000 and 850,000 years old. So now we're going to look through our cross section, take the slice through there. These are the layers of our cake. These are the wells drilled at the Forge site. We've got a bunch of deep observation wells. Then we've got our injection well in blue and our production well in red. Temperatures here. So the goal of the Department of Energy was to get in a plutonic rock within 1.5 kilometers of the surface and be in crystalline rock, right? They were looking for something homogeneous and pretty representative of the continental crust about anywhere you go. You go out to the West Coast, you go under Mumbai or someplace. You get down to temperatures, these are the kind of rocks you're going to see. And I'm going to keep alluding to this strange compositional / lithologic contact that lies right between our injection and production wells that are only about 100 meters apart, 300 feet or so. So, and I should have pointed out that this map is courtesy of the UGS. Stephen Kirby and others put it together for us in the early stages of the project. Tectonic history, we're all from Utah. We know this, the basin range is pulling apart. We're going to go from early, kind of intermediate early to present day right here. Our cross section came from right within that yellow square. Another version of the geologic map. What I really want to show on here is that there's this brittle ductile transition. This is happening. Brittle ductile transition right here at about 400 degrees C. These are myelinites as drawn. They're brought all the way up to the surface here, still occurring at depth. And due to this extension, we have a regional fracture pattern, which is mapped here by John Bartley. These are all his figures. And we have this overprinting fracture set that's exposed both in the Mineral Mountains, as you see in outcrops here from these yellow squares, and within our reservoirs that we see in the FMI wells. Okay, so we're drilling into a Pluton. Here's an example everyone's familiar with. Right, this is El Capitan in you know what? I don't think I ever took the voiceover off this. You can see my cursor going crazy. El Capitan. Right, you got about 3,000 feet of exposure here. You probably saw that fella climb this with no rope. And you can see a simplified geologic map showing ages of emplacement. This was all put together over 5 to 6 million years. Then if we come in here, you can see the real nitty-gritty detail. And if I just happen to overlay our injection and production wells to scale on this thing, you can see that we kind of whole thing if, you know, the National Park Service let us set up a drill rig up top. And we're going to go through all sorts of lithologic complexity as we go through here. And I would argue that this is an even simpler Pluton than we see in the Mineral Mountains of Utah. Okay, so the main tool of a geologist when you're drilling a well are cuttings. It's a semi-continuous record of what's come up to the surface. You're going to catch them about every 10 feet. And what you can see here is that we've been cutting through this granite like you wouldn't believe, faster and faster with time. This is our initial well. You get a whole preview here. Our initial well is 5832. We were making like 10-ish feet an hour. We were using these regular tricone, roller cone bits, kind of the industry standard at the time. We tried that Chimera bit, and then we settled on these PDC bits. And they are cutting through that like you wouldn't believe. Everyone's happy about it but the geology team. Okay? Which is basically, this is what the rock looks like when it comes back. You just pass that. We got fine sand. So now you're taking those core samples I've laid out on the table and trying to reconstruct them from that Humpty Dumpty bit there. It's challenging to say the least. There's some textural contrast in here we'll get to later. But here's some chipboard images. You're just showing the lithologic variation in different colors as you're going down. So you got the basin fill kind of in brownish. Then we're getting into different flavors of the Pluton. And in here we even get into some metamorphic rocks with that. Okay, so here's where we're going to talk about kind of changes in lithologies. So these are ternary diagrams where I plot normalized abundances of quartz at the top, alkali or potassium feldspar where A is, plagioclase feldspar over where B is. Okay, and then it's going to fall into some field. It's probably hard to see. The biggest one here is granite. So in general, most of the shallow rocks make an L-shaped trend going from granite down to monzonite. But they're color-coded by depth on this, and what you can see is that when you get to 7,000 to 8,000 feet or deeper on a bunch of these wells, 78B, 56, and 16A32, we're changing composition in the deepest part of the reservoir. 5832 didn't make it that deep. It was only 7,500 feet deep. Then we've got some wells from Roosevelt Hot Springs plotted here where we see something similar. But I want to point out this lack of lithologies here. Right, we're seeing this compositional change in 16A at about 8,000 feet. We're getting into a different rock type below that, but we're not really seeing it over here in 16B. And they are, keep in mind, only 100 meters apart. Here's something similar. Okay, I'm going to be talking a lot about lithologic complexity and variability, but the reality is they're made of the same handful of minerals. We got quartz. We got plagioclase feldspar, potassium feldspar, and in gray I have other primary minerals. It's going to dominantly be biotite, hornblende, clinopyroxene, titanite, and then your other accessory minerals, so on and so forth down the line. I've also plotted secondary minerals in pink. These are primarily clays and carbonates here, which are seen in the reservoir. A little bit of epidote, actinolite, high temperature stuff. It's not expected to form at current reservoir conditions. And right here in these two wells where I have the yellow arrow, I mark the contact between kind of granitoids mixtures and mixtures of granitoid and mostly gneiss, a little bit of marble and quartzite every once in a while. But at these contacts, we have major fracture zones filled with a lot of secondary minerals. And in fact, this one in particular has a lot of plagioclase and quartz, so it'd actually be a lot, actually it's this one. Actually be a lot larger if I included all this. So at contact between different lithologies, we see big fracture zones. Here are the geophysical logs from the contact in 16A. So when we have travel time increase, density drop, porosity increase, and the resistivity measurement at 10 inches seems to do a good job of finding these fracture zones. These are major fracture zones, thick fracture zones, not just this guy or some other examples I have up here if you want to come take a look afterwards. So multiple, anastomosing fractures here. Many of them are there, so we see the large scale ones. The yellow one highlighted, this is a thin section from it. What you're seeing are ROMs of carbonate minerals. These are magnesium iron-bearing carbonates, and they're in this fine-grained matrix of microcrystalline quartz. So we are very fortunate to have a whole bunch of core from the Freeze-Off Forge project. I brought some examples out here. We have, I say about 250 feet of core collected from all the different wells in the field. These are some examples of some nice stitched together images. This was done here at UGS. So you're taking the entire cylinder of the core with pictures at 360 degrees and laying it flat, kind of like a well log. This one was taken really shallow in 16A, got broken and bleached and altered, granite at the top, where we get into a pretty thick myelinite down here. I've got an example of that on the table. Sometimes we'll go through pretty homogeneous rock, like we're seeing here, and some granite. And then we get into some metamorphic rock where it just is incredibly variable, even at fine scale. These are the only age dates we have from the field. So this is a core taken in our pilot well, 7,500 feet deep, 5832. You can see a banded diorite. It's been dated at 10 million years old. And it is in a wall rock of 22 million year old. There's a quartz monzonite, I believe. Or maybe I can just look at the legend. That would probably tell me. Granite, quartz, no. All right, so now we're looking at the fabric of the rock. So we've taken thin sections, either horizontal or vertical orientations in reference to the core. You can see the banding shows up really well here, really fine-grained rock in this diorite, the banded stuff. Then we're going to move down into the granite, and it looks completely different. More core examples. So now we're looking at our production well, 16B. We got the shallow vertical section. That's here in the light colored stuff. This is bleached and altered. It's right up near the top of basement. It was adjacent to a normal fault that's now been rotated to about 25 degrees. Jump down here to 9,800 feet where we're coring through one of our stimulation intervals. Dark colored rock. Move down 400 feet. We're into some light colored stuff. Move down another 200 feet. We're in a completely different rock. And there are examples of that on the table. So we've got plutonic rock and we have this metamorphic rock. There are no distinct minerals in this metamorphic rock, but as you can see, it's got a pretty good texture here. Dark band is a myelinite. We have these nice algons. And I brought this particular along. Just move that around. So we've got shearing. We've got the mineral grains getting smaller and smaller the more they've sheared. Who knows how much slip has been accommodated by the stone. But it's moved past each other, squished down, become really fine grained. With the exception of some of these feldspar crystals, which are a little more resistant. And on this side, we have some photomicrographs, both playing across polarized light. So now we're distinguishing between metamorphic rock and plutonic rock, which is, mineralogically, there's no distinction. There's no obvious distinction. Every once in a while, I'll get a trace of garnet or a trace of slimonite, but it's very rare. But you can see they're intensely developed metamorphic textures in these rocks. So these rocks started their life somewhere in the middle crust through extension. They've been pulled up to the surface, rotated. Now they're sitting within a couple kilometers of the surface. This is a picture of a myelinite, and what you're seeing here is that with strain and as we get harder, first the biotite's going to start to get squishy. It's going to roll out, spall off, make finer and finer grains. Then we're going to get in the quartz, and feldspar is the last one to start getting soft. So we probably got up in here to the 400 C plus range, and we were singing this thing with a little crust. Okay, this is a bit of a primer on natural fractures and how they played a role in the creation of our EGS reservoir. Good. So we're looking at the toe of our injection production pair. We're kind of enlarging it here. We have casing most of the way down these wells. These are open hole sections. And then where these discs are is where we've done plug and perf operations to do hydraulic fracturing. And try to make our man-made EGS reservoir in these hot, dry rocks. Okay, so kind of keep this in mind. We're going to move to John's favorite figure here. Okay, so we have stages 3, 4, and 5 all connect to make this corridor. These all merge. We have one, I'll show you on the microseismic in a minute, one main corridor here. There were attempts to frac here and here, but we didn't get enough flow rate to start adding proppants. So those have remained unviable. And then we go up here to stage 3 where things really, 8, excuse me, where things really start to get interesting. You start stimulating here. So in an isotropic rock, in this stress field, we expect hydraulic fractures to be in and out of the plane here, vertical like that. So the idea was we oriented the wells so that anything we built would be perpendicular to the wellbore. But these guys start fracturing way up the hill, all the way up there. And then with time, start moving back this way. Move up the hole, start stimulating stage 9, shoots up into the same direction. The frac hits overlap on the fiber that's installed in this well. Go up to stage 10, same thing happens. So we have 2 dominant kind of fast tracks to our reservoir, which is not exactly ideal. And superimposed on top of this are the readouts from the pressure temperature spinner logs, where you can see that 25.8% of the water being produced comes out in that section. 48 or so comes out of that section. We couldn't get it any further down the well than this, but a little more than a third is coming out in this bottom part. Do the same thing with injection. You can see where it's coming out of stage 10, stage 9, stage 8, nothing in 7, nothing in 6. And then about 30% of it's coming out of the bottom here. So what's happening? It's not behaving as we expect in a hydraulically fractured rock that doesn't have any weaknesses in it. We know there are pre-existing planes of weakness. This is data from the FMI log showing the largest aperture fractures that were measured. And by large, I mean a millimeter-ish, maybe a couple millimeters. And you can see they overlap really well with where we saw frac hits on the production well. Here's a view of the microseismic data. We've got 3R, 4, and 5 making a plane sort of here. So here we're looking north, here we're looking down. This is where we're getting about a quarter to a third of our flow moving through the reservoir. Then we move up here to this planar seismic feature. This is where we're getting 3/4, 2/3 of our flow moving through the reservoir. Right on time. This is what we want it to look like. If we could build a tube and shell kind of radiator and stick it in the ground, that would be ideal. Equal spacing, we want conformance, equal flow through there. We want to efficiently mine this rock as best we can. Because once the heat in this rock is out, it's going to take, according to Peng Ju, about 1,000 years for it to regenerate. Got to get one shot at it. Okay, moving on to veins. This is the fattest, juiciest vein we found in the reservoir, in core. About 1 centimeter. It is not quite completely filled. There's some pockets on the outside. So it's got some remaining permeability, but no porosity. They're not interconnected. That is a fat target. And luckily it shows up pretty well on the FMI log here. The mineralogy of this vein is pretty wild. So this is a saddle dolomite. You can see these curved crystal faces and curved cleavage planes in there. These kind of Morphologies have been reported from SEDEX deposits, Mississippi Valley type deposits, and hydrothermal dolomite hydrocarbon reservoirs. And in all of those places, fluid inclusion analysis says that these are hot, overpressurized, upwelling brines. How you get a magnesium-rich water in a pluton is kind of beyond me at this point. Magnesium is usually one of the first things that fall out of a hydrothermal fluid. You're going to be making clay minerals, chlorite, smectite really fast, and also things like that. So how you source something deep that's rich in magnesium and bring it up to the surface, maybe even hydraulically frack it up, if it's the same, is a mystery. Luckily, I don't know if you can see it here, but there are trains of primary fluid inclusions. I haven't gotten around to it yet, but I'll heat and freeze this and be able to say about what temperature these minerals formed and about the salinity of the water from which they precipitate. Okay, more veins. That is more typical of a vein in the reservoir. And the modelers tell me that the veins we've made are about on a millimeter scale. So we're talking about pushing water through these rocks. These apertures are tiny. And good luck seeing that in any sort of geophysical law. It's not going to happen. So we get a variety of minerals here. They're kind of cut off. We got actinolite, albite, high temperature minerals that aren't expected to form under moderate temperatures. Those are what are in the orange box here. So they were early. They kind of cracked on their way up to the surface when temperatures were hotter as they were being exhumed. But then we get into these minerals, which we're expecting. We're seeing interlayered clays, chlorite smectite, illite smectite, some fine-grained silica. Might be precipitating as, an amorphous phase or like an opal CT or something. And then what's really intriguing is halite. So here's some photomicrographs in plain and cross-polarized light of a vein that's got 3 generations of infilling. You have early chlorite, it's sealed, broke again. You get chlorite smectite, which is this kind of, mottled colored stuff. And then the last generation is illite smectite vein that fills the middle, and that actually contains halite crystals. So what I'm showing here are the flowback stages from the first 3 stimulations. We injected through the open hole, water sat down in there for 12 to 24 hours, came back, and these are time series analyses where you can see that we injected this drinking water and it got progressively more saline as it came back over really short time periods. You wouldn't think a granite with aluminosilicates and quartz would be all that reactive. But we've seen rapid and substantial changes in chemistry over really short time periods. Okay, looking for halite in a thin section that's been cut and polished in water is not really ideal. So here we have a broken piece of core, snapped in half. We're looking at SEM images of it over here. So right now you're seeing a clay mineral on its side, this hexagonal plate, and a lot of this furry stuff are the clay minerals on their edges. And we're looking at an EDS map. And it's kind of hard to pick out because these things are tiny, but this little square here is green here. Some of this other lighter BSC colored stuff is also popping out in green. Those are registering really high in chlorine and sodium. So we're pushing this water into the rock. I should also mention that we just crushed rock, just pieces of core with no veins, interacted it with water, no change in salinity to speak of. Okay, so if we're picking up salts in this water, in this reservoir, and there's no porosity or permeability to speak of, well, why isn't it coming out of these natural fractures? So I hope that gave you a glimpse into what I'm wrangling with lithologic complexity, changes in plutonic phases. I should have mentioned that the Mineral Mountains is kind of famous in some circles for magma mixing, felsic and more mafic lavas coming together. It's been assembled over a time span of something like 8 million years. Then you've got this overprinting, metamorphic overprinting as it comes up to the surface, also putting that brittle, well, first ductile with the fabric, then brittle with fracturing. And now we're trying to make an EGS reservoir out of it. So think that takes me to the end. I don't know if we have time for questions or anything like that, if we're just moving on, but if you want to come up to me afterwards, I'd be happy to discuss anything with you.